In this video, we're going to walk through an example to construct a 95% confidence interval to estimate the difference between means from two independent populations. So the example we're going to take a look at is an example where we've got students that are taking notes either by hand or using a laptop, and then we want to see whether their method of taking notes by hand or by laptop has any correlation between their scores on a test. So what we can see over here from this table that summarized our samples, there were 38 students assigned to a group that were taking notes by hand, 40 that were taking notes using a laptop by typing. And we can see that the mean score for those by hand was 25.6 compared to 18.3 for the laptop group, and we've got the standard deviations from each of those samples. So in part A, we want to find the 95% confidence interval, and we're going to do this using a t-distribution with degrees of freedom that we find using the casual approximation, where we're going to let the degrees of freedom be the minimum sample size minus 1. Okay, so the general formula for that confidence interval we found on the previous slide, that would be the difference in our two sample means, x bar 1 minus x bar 2. So that's where we would start our estimate. And the lower estimate, we're going to go t alpha over 2 times our estimate for the standard error, which is s1 squared. We'll take the s1 squared over n1, and then we add to that s2 squared over n2 and take the square root. So that gives us the lower bound for our difference in population means, and the upper bound we get by just adding that margin of error. So we take the x bar 1 minus x bar 2 plus t alpha over 2 times our estimate for the standard error, which we get by taking s1 squared over n1 plus s2 squared over n2. So for us, finding x bar 1 minus x bar 2, we would just take the difference in these two values, and that gives me an estimate of 7.3. So my initial estimate for this difference would be 7.3. Then, using the standard error, we can build some error into our estimate. So to find that, we would use the standard deviations for our sample and their corresponding sample sizes, and you can check that this standard error comes out to approximately 2.257. And for the t alpha over 2, since we have a 95% confidence interval, we would use the qt function with 0.975 as the area to the left. And here we're going to pick 37 degrees of freedom because the smaller of our sample sizes was 38. And so picking the smaller of the two, which is 38 minus 1, gives me the 2.206. And then plugging these values into their corresponding places, we get that the lower cutoff is 2.727 and the upper cutoff is 11.873. So that would be our 95% confidence interval using this estimate. And let me just say, if you didn't have R available to you and instead you were working with a t-distribution, let's flip over to what that t-distribution would look like to show where you might get that estimate. Okay, so if we want to interpret what this interval tells us, over here we could say that there's a 95%, the interval from 2.727 up to 11.873 contains the actual difference between the mean scores of all students that take notes by hand compared to all students that take notes with a laptop. And if we want to think about, well, does this seem to indicate that there's a difference in the exam scores between the two groups? Notice that this interval consists of only positive values, and 0 is not in here. So it does not seem plausible that 0 would be a good estimate for this difference. So we actually have pretty good evidence to believe that there is a significant difference in the exam scores between these two groups because this interval contains only positive values. So it seems like the only plausible estimates would be that the by hand group does better than the laptop group. And so for the very last part, C, I just want to compare the result in C, which is the more precise estimate, with the one that we got in A, using the more informal estimate of let's just pick the minimum sample size to determine degrees of freedom. So if you actually use that really complicated formula for Welch's approximation for the degrees of freedom, that works out to be about 72. So if we were working with part C, what doesn't change is we're still going to use these values for our difference in means and the standard error. And what is going to change is the value for T alpha over 2. So in that case, the T alpha over 2 you would get by using that QT function. The confidence interval was 95%, so we're going to choose a quantile of 0.975, and now we're going to plug in 72 degrees of freedom as opposed to the 37 that we used the first time. And when you plug that in, you get a T alpha over 2 value of 1.993, okay, which is different than the value we got over here when we picked the minimum of the two. But they're so close to each other, and in fact, if we were to take these calculations out and use the same formula up here, and all we're doing is changing the value for T alpha that we have, or T alpha over 2 that we have here and here, we're now going to use this more accurate estimate. In the end, what our confidence interval would work out to be would be 2.802. Less is the lower bound for this difference, and the upper bound would now be 11.798. So if we compare this to the estimate that we got up here when we were a little more casual with our degrees of freedom, there's not much of a difference between these two. So at the end of the day, we're not losing too much by making this assumption that let's just pick the degrees of freedom to be the smaller of the two. But if you want to be more precise, then you certainly can use Welch's formula. And so let me just say in closing, there would be no way to use the built-in t-test formula in R to do this one, because that works when we actually have the raw sample data like we did for North Carolina births. Since in this example, all we have is summaries of the two samples, we would actually need to do these calculations ourselves, and we couldn't just depend on R. So in some of the problems that you're practicing, you may be able to use R if the data sets are already loaded into R. In some of the problems, you may only have summaries of those data sets and not the data sets themselves, in which case you're going to have to walk through the formula like we did in this example. And so if we wanted to use the T table to estimate the value for T alpha 2 in the example where we were comparing students that were taking notes by hand versus a laptop, in that case we had one sample was size 38 and the other was size 40. So for the smaller sample, the degrees of freedom should be 37. But if you notice here, 37 is actually not on the table. So when you're working with the table and you're giving some estimates, you want to err on the side of caution. So the side of caution means the smaller the degrees of freedom, the fatter the tails of the t-distribution. So rather than use 37, which we don't know, the choices would be to use 38 or 36. We're going to choose 36 because it's smaller. And then we would come across and we have a 95% confidence interval. So using the table, our guess for T alpha over 2 would be the 2.028. And let me just say from R, we got an estimate of 2.026. So this table, that's going to give us a pretty accurate estimate if you don't have R available.